Welcome to our deep dive into WebRTC system design, specifically focusing on video conferencing architecture. WebRTC, or Web Real-Time Communication, is an open-source project that empowers web browsers and mobile applications with real-time communication capabilities via simple JavaScript APIs. Essentially, it allows for peer-to-peer audio, video, and data transfer without the need for proprietary plugins or complex setups, revolutionizing how we connect online. Prior to WebRTC, achieving real-time communication in a browser often required third-party plugins like Flash or Silverlight, which presented significant security vulnerabilities and usability hurdles. WebRTC eliminated these barriers, integrating real-time communication directly into the browser's core. Understanding its underlying architecture is paramount for anyone looking to build robust, scalable, and high-performance video conferencing solutions. It's not just about making a video call, it's about designing an entire system that can handle diverse network conditions, varying numbers of participants, and maintain a seamless user experience. This module will demystify the core components and architectural decisions that make modern video conferencing possible. At its heart, WebRTC relies on three fundamental components to establish and manage peer-to-peer connections: signaling, interactive connectivity establishment, ICE, and the RTC Peer Connection API. Signaling is the initial handshake, a mechanism used to exchange metadata necessary to set up a call. This includes things like session descriptions, network information, and control messages. Crucially, WebRTC itself does not provide a signaling server. Developers have the flexibility to implement their own using protocols like WebSockets or SIP, making it highly adaptable. Once signaling is complete, ICE takes over. ICE is a framework that helps WebRTC peers find the best possible path to connect to each other, navigating complex network topologies like network address translators, NATs, and firewalls. It uses stun and turn servers, which we'll discuss shortly, to achieve connectivity. Finally, the RTC Peer Connection API is the central hub where the actual media streams are managed. It handles the encoding and decoding of audio and video, manages network jitter, and ensures secure, real-time data transfer. Together, these three components form the backbone of any WebRTC application, working in concert to provide a robust and efficient communication channel. The signaling server is the unseen orchestrator behind every successful WebRTC connection. Its primary role is to facilitate the exchange of crucial session-related information between two peers before they establish a direct media connection. This information includes Session Description Protocol, or SDP, offers and answers, which detail the media capabilities of each client, such as supported codecs, resolutions, and network types. It also handles the exchange of ICE candidates, which are potential network addresses the clients can use to communicate. Since WebRTC itself is client-side technology, it explicitly does not define how signaling should occur. This design choice provides immense flexibility for developers. They can choose any messaging protocol and transport layer they prefer, such as WebSockets for real-time bidirectional communication, or even more traditional methods like SIP or XMPP. However, WebSockets are particularly popular due to their ability to maintain persistent, full-duplex communication channels over a single TCP connection, making them ideal for the rapid exchange of signaling messages. The signaling server acts as a temporary intermediary, ensuring both participants have the necessary information to initiate a direct peer-to-peer WebRTC connection. Once the direct connection is established, the signaling server's direct involvement in the media flow typically ceases, though it might remain active for call control messages like hanging up or muting. One of the most significant challenges in establishing peer-to-peer connections is navigating network address translators, or NATs. Most devices on the internet sit behind a router that uses NAT, which translates private internal IP addresses to a single public IP address, making direct connections difficult. This is where stun and turn servers become indispensable. Stun, or Session Traversal Utilities for NET, servers help WebRTC clients discover their public IP address and the type of NET they are behind. A client sends a request to a stun server, which simply echoes back the client's public IP address and port as seen by the stun server. This information, called a reflexive candidate, is then shared via signaling, allowing peers to attempt a direct connection. However, some restrictive NAT types, particularly symmetric NATs or corporate firewalls, might block direct peer-to-peer connections even after stun has provided public IP information. In such cases, turn or traversal using relays around NAT servers come into play as a fallback. A turn server acts as a relay, forwarding all media packets between the peers. Instead of a direct connection, both clients send their media to the turn server, which then relays it to the other party. While effective, turn servers consume significant bandwidth and processing power as they are actively involved in the media stream, unlike stun servers. Therefore, turn is typically used as a last resort when stun and direct connections fail, ensuring connectivity even in the most challenging network environments. The process of using stun and turn within ICE is crucial for robust WebRT connectivity. While WebRTC excels at peer-to-peer connections between two participants, scaling to group calls with 3 or more individuals introduces significant complexities. In a true peer-to-peer mesh network, each participant would need to send and receive media streams to and from every other participant. For a call with n participants, each client would need to manage n-1 outgoing and n-1 incoming streams, leading to a total of n times n-1 streams in the network. This quickly overwhelms client-side bandwidth and processing power, making group calls impractical without a media server. This is where media servers, specifically SFUs and MCUs, become crucial. An MCU, or Multipoint Control Unit, operates by receiving all incoming media streams from participants, decoding them, mixing them into a single composite video and audio stream, and then re-encoding and sending this single stream back to each participant. This approach significantly reduces the client's outgoing bandwidth burden, only one outgoing stream, but places a heavy computational load on the MCU server due to the mixing and transcoding. In contrast, an SFU, or Selective Forwarding Unit, is a more bandwidth-efficient and popular choice for modern WebRTC conferencing. An SFU receives each participant's incoming media stream and simply forwards it to all other participants without decoding or mixing. Each client still sends one outgoing stream, but receives n-1 individual streams. While this increases the client's incoming bandwidth requirement compared to an MCU, the SFU itself is much less CPU intensive because it doesn't perform complex transcoding or mixing. SFUs are generally preferred for their scalability and lower server resource demands, enabling larger and more dynamic group calls.